AXIS is the Advanced X-ray Imaging Satellite, which is NASA probe mission. It's about $1 billion in terms of projected costs. NASA has selected basically two probes. AXIS is going to be probing the high-energy X-ray universe, so it's sensitive to X-ray light. The competing probe is going to be sensitive to the infrared. We're excited about AXIS because it's supposed to be the follow-up to Chandra. So Chandra has been launched in space since 1999 by NASA. Chandra has enabled us to zoom in on the workings of very exotic compact objects like neutron stars and black holes. It's getting really old, and we didn't have anything planned for the 2030s and beyond for the next generation in terms of high-resolution X-ray astronomy. So AXIS is going to fulfill that. It's going to have very high angular resolution, which means if you had AXIS eyes, you could read a newspaper from kilometers away. The field of view of AXIS is going to be about the size of a full moon, and it's going to be also 10 times more sensitive than the Chandra X-ray telescope. So one of the things we're planning is to do a survey of the Milky Way, the galactic plane in particular, which houses the supermassive black hole in the center of our own galaxy, as well as lots of star formation regions and regions of star death. We're not just improving on the angular resolution or the sharpness of the images. We're trying to do that across the field of view, which allows us to see sharply in the whole field of view. I guess with AXIS, you get a bonus mission, which is placing the Swift Observatory, which was named after the scientist who really pioneered the field of gamma ray bursts. So NASA selected this probe just this past November. The team was awarded $5 million to use for the next year and to improve on both the science case and to demonstrate that the technology will work to achieve the science we're promising. So NASA will make the final selection among these two probes in 2026. And the goal is to launch the mission in mid-2032. We have 1 year to actually demonstrate both the technology and expand on the science. I'm interested in understanding what happens to stars after they die and how they impact their environment, their surrounding, how they impact the evolution of galaxies, including our Milky Way galaxy. Chandra showed us that when massive stars die, they form these fascinating objects called neutron stars or pulsars. Chandra allowed us to discover a whole new class of such objects that are to date only seen and visible in X-rays. The first one actually was discovered with the first light Chandra observation. It's the neutron star at the heart of the brightest and one of the youngest known supernova remnants in our galaxy called Cassiopeia A. This is an image made with the Chandra X-ray Observatory of this young supernova remnant. So what you're looking at here in color are the remains of this exploded star. And those colors reflect the different heavy elements created. Those elements have been cooked in the star before it exploded. As the star is burning fuel in its interior, hot interior, it's making heavy elements. And those elements are going to be scattered in space once the explosion happened. So those colors reflect elements like silicon, sulfur, calcium, and iron, the elements that make you and me and everything in the universe. There are other objects like this very pretty nebula called the Crab Nebula. So what you're looking at is this cloud of highly relativistic particles shining in X-rays and emitting this radiation that we call synchrotron radiation. And this blue image that you see is all X-rays, and it's only Chandra that allowed us to see this fine detail. So we see rings, we see jets, and all of this is shedding light on what happens to objects like massive stars when they die, but how they interact and energize the surrounding medium. This is one of the most studied astrophysical objects by the community, and it still fascinates us. But this Chandra image is the first to really reveal the inner workings of fast-spinning neutron stars. So with AXIS, we're going to not only find more such objects, we're going to go deeper, not just look at our Milky Way galaxy. We're going to look at nearby galaxies and beyond to find more of these objects, which tell us about star formation, not just in our own Milky Way, but also in other parts of the universe. I actually care about all these other wavelengths, but I can't imagine having a future in astronomy without high-resolution X-ray. We're very excited in this large collaboration, which also includes people from outside the US and Canada, including from Europe. It just sparked a lot of interest in the community, and lots of people really are very keen in making Access win. We hope that we can involve many more people from Canada, because this is about the future of the next generation who really cares about high-energy astrophysics, but also about data science, because there's multiple surveys we're planning, but the one I'm involved in is the Galactic Plane Survey. It's going to lead to millions of sources. It's going to introduce lots of data. We're going to need new innovative techniques. We're going to have to collaborate with statisticians, computer scientists, to be able to introduce those new techniques to analyze data. We already have a large group from the University of Manitoba really involved and playing a leadership role in Access. So I'm very excited for my group members to be part of it as well. I can really see this to be a great opportunity for us in Canada to lead in high-energy astrophysics and to also shape the future of the next generation of scientists. Access is going to be representative of the science interests of the community, and hopefully will demonstrate that the future of X-ray astronomy is going to be bright and lead to discoveries that hopefully shape the future of the next generation.